All right, so the first substantive lecture that we've got, getting into the actual nuts and bolts of the surveying material, is going to cover a fair amount of basics, get through a bit of nomenclature, some definitions, and then a couple of examples of the types of things that we're going to get into a lot more detail throughout the term. So let's go ahead and get into it. So we do have a fair amount of topics to cover with this lecture. It's kind of a survey, no pun intended, of a lot of different topics related to this class. And that's kind of the structure of what we're going to be faced with this term. We've got a lot of different topics. They're all stitched together with common themes, but it's going to be pretty broad and diverse. And so one day we'll be talking about satellites, and the next day we're going to be talking about chains. The surveying technology has really changed quite a bit over the years, as you'll see with these introductory slides. And some of what we're going to be talking about is very traditional type measurements, and then we'll also get into the more detailed contemporary type technology. So we'll be jumping around a lot. Just bear with me. It's all relevant, especially for the FE exam, but sometimes it gets a little bit odd the way that we're jumping back and forth. So I appreciate your understanding with that. We'll do some basic introduction at the beginning, then we'll get into some more detailed discussion about measurements and things like that towards the end of the lecture. So we do have the threshold topic of what is surveying. So like I just mentioned, surveying has to do with satellites and GPS, but it also has to do with things like pacing, pretty much the oldest type of surveying technique that you could do. What is surveying then? So the definition out of your book is pretty good. It's the art and the science of measuring angles, distances, and positions, which you could think of as like coordinates on or near the surface of the Earth. And so we're primarily concerned with things that are reasonably accessible by civil and environmental infrastructure type projects. But mines and things like that would be relevant for surveying. Skyscrapers would be relevant for surveying. But that's only a very thin layer towards the surface of the planet. That's what we're primarily concerned with, and that's why some of the aspects of what's known as like geodesy, determining a good approximation for the shape of the Earth is so important, and that's some stuff that we'll get into a little bit later on. But we're primarily talking about measuring geometric properties at or near the surface of the Earth, primarily. So, what are we using surveying for? What is the point of learning about survey? And what do professional land surveyors do on a regular basis? Well, one thing that most people think about when they hear surveyor, they think, oh, well, they're going to go out and take a bunch of measurements of what's already out there existing and then prepare a map or a plan of it. So they would go out with their equipment. Oftentimes nowadays that would be a total station, sometimes with GPS and robotics to help streamline that effort. They'd go out, they'd measure elevations, features like where's the storm sewer, property lines, things like that. If there are monuments out there, they'd collect all of that data, they'd bring it back to their office, and then they would prepare a map, an exhibit that shows all of that data that they collected. That's what most people think about for surveying. But there's also an important characteristic of surveying that goes in the other direction. So let's say that somebody has created a design of a building or a water treatment facility or a retaining wall. When we've designed it based off the survey, we then need to hire the surveyors again to go out and stake out maybe important features of our design so that the contractor can go out there and actually build it. Where is the corner of that building that you want built? They need to go out there, they'll put grade stakes in for changing the geometry of the surface of the lot. They'll also put in stakes so that you know where the corner of the footings are. It gets pretty detailed, but surveyors are involved at both sides of the project at the get-go so that we know what the existing conditions are, and then on the back end so that the contractor knows where to actually build things. And during construction as well too. I've worked on some pretty complicated projects where we had surveyors out pretty much every single day measuring how the geometry of our bridge is changing as we add pieces here and there. So from a construction services standpoint, a lot of people don't think about that, but it is an important role that they play in the civil infrastructure project cycle. So what are the types of survey? We know that there could be surveys for collecting existing information or putting out stakes and things like that for a future design. But in between, there's a lot of other types of survey as well that we need to get into. So a common big picture difference between different surveys would be either a plane survey or what's known as a geodetic survey. So when you hear plane survey, what we're talking about is that we've taken the curved surface of the Earth. The Earth is not a perfect sphere, it's known as an oblong spheroid, and we've tried to approximate locations on the surface of the Earth with a two-dimensional plane. Now, sometimes that two-dimensional plane is kind of like the side of a cylinder that we kind of wrap around the Earth, and then we can unwrap it and turn it into a flat two-dimensional projection. But in one form or another, we project a plane that can be represented easily in two dimensions, and that's how we take our measurements. Now, it's not correct. Here's an example of what's known as the Oregon State Plane Coordinate System, and you see all of these rectangles here. These rectangles are actually like small cutouts of a large cone, and then we wrap it onto the Earth. And the reason that we have so many of these is that we want a 2D projection so that we can put it effectively on a map, and so that measuring locations are relatively easy. We actually provide like a coordinate in terms of just two different distances called a northing and an easting. It's much easier to deal with than trying to define everything in terms of latitude and longitude. That would be really difficult if we were trying to lay out a construction line on a project and we said, go to this latitude and longitude, and then go to this latitude and longitude. It's much easier for us to say this many feet to the east, this many feet to the north. That's commonly how we do it. But so plane surveys are getting a northing and an easting from a grid system that is approximating the curved surface of the world with a two-dimensional rectangle or kind of rectangle. Geodetic surveys don't make that abstraction. They take into consideration that curved surface of the Earth, and so there's less distortion with the geodetic survey. A plane survey inevitably has some error or distortion. The larger those planes are, the areas are, the more distortion you would get. And a geodetic survey takes into consideration that curved oblong spheroid shape of the Earth. And what you often see is that really big surveys with large distances in between usually take the geodetic survey approach, whereas smaller projects like buildings or even streets and some highways too often are using a state plane coordinate system. But on the bottom right, you see an example of a monument, a survey monument from a geodetic survey that the United States does. And if you go hiking at the top of mountains, you'll often see discs like this, and it says specifically geodetic survey, and that's because this is what was used to lay out a lot of control points across the United States. We're talking about hundreds and thousands of miles apart, and so doing plane surveying would be untenable because we get large errors at that very large distance, and so we take into consideration the curvature of the Earth then. All right, so within these two different types, plane surveying or geodetic surveying, we can talk about other types of survey as well, kind of subsets of survey. So control surveys tend to be bigger reference type surveys. We use these to then act as a benchmark for other smaller surveys. So a city might have a control survey that you would base property surveys off of, things like that. So it's like a control system that other surveys are going to be based off of. They need to be very precise. They're often over large areas as well, and oftentimes things like property survey and definitions will be based off of it. So here's an example of a control survey done by the city of Portland. This is a vertical benchmark. You can find these on the sidewalks kind of all over town. And this is what is often used for setting, vertical geometry for surveys across the area. Preliminary surveys, this is kind of like the idea of going out and getting that data of existing conditions to then provide it to a designer. Oftentimes we call this a topographic or a feature like utility type survey. Oftentimes we'll have the surveyor go out and capture everything that's relevant to our project. So that could be the existing ground elevation, which would be a topographic survey. They might go out and collect bathymetric information or hydrographic surveys, like what is the surface of the water, or what is the contour underneath the water of the riverbed or the lake bed. Utilities are often picked up at this point as well too. So this is gathering the data to allow designers to then do their work. And so that would be, I mean, a lot of times nowadays that would involve GPS and robotics. So here you see someone working with a rover station with GPS, and these are quick and accurate enough nowadays to often take the place of a much more complicated piece of equipment. And then layout surveys, this would be that construction service that we talked about where the design is completed. Then the surveyor would go out with the plan set. They would put oftentimes stakes like this to either help with grading of the site or to identify the corners of foundations, the locations of utilities, things like that. And nowadays you actually can see a lot of GPS at this point as well too. So I think I have a photo a little bit later on as well where a grading piece of equipment, like a bulldozer basically, has like 2 GPS antennas on top of it, and we can actually like apply surveying workflows to automate where those pieces of equipment are going to grade and like how, what elevation they need to grade at. So we can actually start controlling equipment using surveying techniques to automate them, very much like we're seeing with other like automotive spaces as well. All right, so what within surveying, I mean, we've talked about different types of surveys. Within surveying, just like within civil engineering, there are a lot of kind of subtopics or specialities that surveyors can get into. So I just pulled up a website of a local surveyor. They happen to do a survey, property survey of my house recently, and I just pulled up their website to see, what kind of surveying services do they offer, because not all surveying is exactly the same. So they have a list and they say court exhibits, condominium plats, hydrographic work, lot surveys, court and boundary disputes, construction layout, boundaries, topographic. So there's a bunch of different types of surveys, and sometimes the surveyors are specialized in one or the other. Sometimes they'll be more of like the Subaru Outback of surveyors and try to offer everything that people want. Property surveys, getting the legal definition of a property, and then putting down stakes to show where your property boundaries are. That could be one, or going out and then platting out new properties as maybe part of a subdivision. Topographic surveys, going out and collecting the existing ground elevation data that's oftentimes used when we first start laying out civil type projects. Route surveys, that's where you have a long and relatively narrow path. It's often done for highways, pipelines, train, railroads, things like that. Aerial surveys. Now this could be pretty broad. I mean, this could involve things like LiDAR nowadays. We'll talk about that towards the end of the term in a lot more detail. Might involve, having a flight where we have a laser do distance and ranging. We might have photogrammetry, where we take photos from a bunch of different angles and we use a lot of processing algorithms with a nice fast computer to make a model, a 3D model, just based off imagery alone. There's a bunch of different ways that aerial surveys can be implemented nowadays, especially with new technology. Construction surveys, we talked about that as well. There are some surveyors and they only work on construction projects. Final as-built surveys. So this is kind of like the preliminary survey, but instead of going out and measuring existing conditions so that we can put a new civil project on it that we've designed, this would be after construction is complete. Oftentimes we'll hire a surveyor to go out with the plan set and then mark up the plan set to show what the actual dimensions are. So let's say we design a bridge to be 50.25 feet wide. We give those plans to the client puts it out to bid, the contractor builds the bridge. we want to know how is it actually 50.25 feet wide. So the surveyor would go out and verify, whichever values we asked them to, and then we would have then an as-built set of plans. So maybe they cross out the 50.25 and they say, hey, this is actually 50.28 feet wide if we want them to be that precise. And those are really important just from like an inventory and documentation standpoint. If we need to do service to that bridge down the road, if we have any questions, if there is a structural issue with it, having the true dimensions are really important. Hydrographic surveys, some surveyors just specialize in bathymetry, and bathymetry is simply like a topographic survey, but underneath the water surface. That's one important thing if we're modeling reservoirs, lakes, rivers, things like that as well. Okay, a little bit about the surveying profession. So we've talked about a bunch of different disciplines. I did want to point out that professional land surveyors are licensed professionals. In Oregon, they're licensed through the Oregon State Board of Engineering Examination and Land Surveying, OSBELS. It used to be a long time ago that a civil engineering degree was a pretty easy on-ramp to becoming a professional land surveyor. They kind of used to be the same profession for the most part, but with technology advancing the way that it has been, it's much more specialized nowadays. And to become a professional land surveyor or a professional photogrammetrist, you need to be licensed by the state of Oregon, and they would require a specialized degree or a significant amount of real-world experience and possibly some non-degree coursework as well. Oftentimes there's an on-ramp to some of these licenses if you have a lot of experience, but it's certainly the most common procedure to go through and get a bachelor's degree or an advanced degree to get your license. So Oregon State and Oregon Institute of Technology, their Klamath Falls campus offer a geomatics degree that would then allow you to become a professional land surveyor. But as civil engineering majors, it might be common for you to go out and work on a surveying crew for one of your internships or entry-level work. But primarily what we would be doing is liaising with the sub-consulting professional land surveyors. Sometimes they're in-house as well, and then get data from them, tell them what we're looking for, work with them when they're doing construction services. We integrate with them quite a bit, but most, I'd say 99% of you aren't going to become a licensed surveyor, but you will be interacting with them on a regular basis. There's a lot of support for professional land surveying as well, not only in Oregon, but nationwide as well. So there's a Professional Surveyors of Oregon chapter. There's a national society. The American Society of Civil Engineers has a new institute that's really relatively new, maybe 5 years old, that focuses on utility engineering and surveying, that provides a lot of support. Again, the technology is changing so quickly now with drones as well. And with more powerful computers, we're able to do things that we couldn't do 10 years ago, especially things like photogrammetry, going out and taking just a bunch of photos of a site and then turning that into a 3D model. That takes a lot of computing power and a lot of pretty comprehensive algorithms that we didn't used to have even in recent memory. So a little bit about the history of surveying. So surveying's been around for a long time, pretty much as long as we've been building things. There's been some sort of informal surveying going on, but it started becoming more formalized with like the master builders in ancient Egypt. Some of the tools that they had back then were relatively rudimentary, but used honestly for thousands of years. One's called a plummet that helps find a vertical direction just based off gravity, relying on the tension in a cable, making it straight and vertical. There's also something called a square level that also uses the basics of geometry and gravity to help you find a horizontal line. There were things like water levels as well that came in maybe a few thousand years later that were also used, but this is one of the first examples of a true level. And something called a groma. So a groma is a way of laying out like orthogonal lines, so identifying the edges of a rectangular lot. This is also similar to what's known as like a surveyor's cross. Um, just ways to help lay out, straight lines, which were pretty important even back then, especially with the large public works that the ancient Egyptians were involved with. Also in antiquity, closer to, you know, um, 200 BC, and actually a little bit later as well too. But I mean, there was a big push still in antiquity to find what the circumference of the Earth was. So we understood the Earth was round. We understood that it would be valuable to understand what that curvature is, both for astronomy, but also for many other works. And so um, the nascent kind of geodesy, or the analysis of the shape of the Earth, started with a couple Greek mathematicians. There was Eratosthenes and a couple of other Greek mathematicians. Unfortunately, Eratosthenes, his method has been lost to time, but there's anecdotes that he had actually calculated the circumference of the Earth within a couple of percent using an assumption that the rays of light coming from the sun were all parallel, and then building a tower and then digging a big hole and figuring out how the angle of the rays of the sun changed, et cetera, at different areas along the length of the world. In modern Syria, in the ancient Middle East, about 1,000 years later, there was a leader who started a study to try to revisit that idea. And basically, it's what I was talking about, assuming that the rays from the sun are all parallel, and then using that with known distances across the length of the Earth, people were able to figure out the approximate radius of the Earth within, a couple of percent, which is pretty impressive even back then. So back then, the shape of the world, people were being able to more precisely calculate that. They had a lot of technology for measuring level and plumb and things like that. Distances, there were some rudimentary measures of that as well too. And then we started getting into kind of the first, what I would call, wave of more modern surveying equipment. So examples of this include the Gunter's chain that we're going to learn more about, how to, well, more specifically the steel tape we're going to learn about. But back in the 1600s, there was someone named Gunter who developed the first consistent and precise measuring tool, and we call it Gunter's chain even still today. You can still buy those chains, but most people use a steel tape. So here's an example, Gunter's chains on the left. It's a link of chains. They're pretty typically 66 feet, and it's not a coincidence that calculating an acre is basically calculating 10 square chains. Yeah, 10 square chains, not 10 chains squared. We'll get to that a little bit later on. And then you see the steel tape on the right. If we were doing the labs in person, that would be one of the first labs that you all would be doing, is going out and measuring distances with a steel tape. Again, it's been around since really the turn of the 20th century in earnest, so it's been around for quite some time. There's a surveyor's cross that I mentioned before, kind of an advancement on that ancient Egyptian tool that I showed you before, a way of using sites to identify orthogonal directions, because oftentimes we're doing land surveys, property surveys, a lot of that has to do with right angles. And then transits and theodolites. So here's where we really started getting more sophisticated, using optical magnification along with compasses and angle measurements to then be able to calculate angles much more precisely. We use this in concert with some other tools that we'll talk about in a later lecture to start calculating the long distances with tools like this. So it really, especially the optical magnification, really made a big difference in a lot of surveying technology. But these, I mean, all of these tools right here are, kind of like 17th to 19th centuries when they really came into their own. And now we've got much more sophisticated, computer-based technology that's taken the place of a lot of those traditional technologies that we just talked about. So digital levels and total stations. So levels are meant to help you calculate distances primarily, but you can also use it for measuring changes in height from one point to another. Level means that the optics of it are going to be in a horizontal plane, whereas a total station, you can move the reticle in any direction that you want, so you can measure angles up and down as in addition to left and right. Total stations oftentimes nowadays include like a touchscreen and GPS, and sometimes they include robotics as well too. Whereas a lot of survey crews in the past have been two people. Nowadays with robotics, either robotics with GPS where you only need one person, or robotics and then a total station that will automatically move and follow you when you have this prism that's reflecting this laser or this microwave radiation back to the total station. That's the way that we measure distance nowadays as well. It gets pretty interesting. GPS has been huge, as mentioned that as well. So for a long time, the accuracy and the time to secure an accurate signal was somewhat prohibitive, and plus the cost was sky high. Now we have like sub-millimeter accuracy out of a lot of handheld GPS devices. You still need to let it sit for a bit, and oftentimes you'll use a rover that you move around to different points in concert with a base station that is stationary and can get a much more precise signal. But either way, these rovers and robotics and GPS have really been paving the way for much smaller survey crews that can get the work done more quickly. It's pretty impressive stuff. And then laser scanners and photogrammetry. So here, it might be slightly obscured by my video in the lower right-hand corner, but you can take a look at the lecture slides on your own. LiDAR, you've probably heard the buzzword before. Helicopters or drones or planes going overhead, shooting down lasers, having them bounce back. Depending on how they bounce back, we can pick up all kinds of stuff like water surface, vegetation, ground surface. We have algorithms now that can kind of clean up all those millions and billions of points and take out things like birds and cars and things like that. I used to have a friend when I went to Oregon State. He worked for a firm down there. I think it was Quantum Geospatial. And his entire job was getting these terabyte-sized files on his really old computer back then that couldn't handle it all that well. And he would go through and delete out stuff like birds and cars out of LiDAR data. But this just makes it so quick to go out and get elevation data and vegetation data, things like that, with a lot less cost and a lot less time than going out and doing a full in-person type survey. So it's really made a lot of big improvements to the speed of like how we can get civil engineering projects started. We in Oregon are kind of spoiled. The Department of Geology and Mineral Industries, DOGAMI, through Oregon, a state department, does a great job of publicly making LiDAR data available, oftentimes with pretty good resolution, like down to the foot resolution. But a lot of times you have to pay for that data privately if you really want it. So you might hire somebody to go out and do a LiDAR overpass of your site. And then all of this technology has really led to the big picture theme of geomatics. Geomatics is like a system for measuring and capturing, displaying data associated with survey data, basically. So it's a big system, kind of like GIS is a system, and that's what most surveyors' degree is in nowadays. So there's data acquisition, there's processing the data, there is exporting the data to different users, but it's a big, integrated system. Especially when you have different technologies, combination of GPS as well as total station data, as well as imagery, photogrammetry, things like that. It gets really, really complicated, and it's one big kind of integrated system. All right, so let's talk a little bit about reference systems. So when I say reference systems, I'm talking about how are, like, what are you measuring to? If you go out and let's say you hire a surveyor to go out and do a survey. The question is, what are they measuring, like, distances relative to? Or how do they describe a location? What is the system that they're following? So one possible reference system would be geographic, and that's traditionally what we think of as like latitude, longitude, and elevation would be the most common. So based off the oblong spheroid of the Earth, and then locations based off latitude, longitude, and elevation. We can also have what's called a survey grid system, and that is like what we talked about with this Oregon State Plane Coordinate System. This is very, very common for states. It's much easier to deal with what's called a northing and an easting, which is just like a east-west direction and a north-south direction when we're laying out plots of land and projects, things like that. So usually when we see like a survey point for a civil engineering project, it wouldn't be a latitude and a longitude. Traditionally, something like that would be what we call a northing and an easting. We'll talk about that in a lot more detail down the road. Surveyed legal reference. So oftentimes when it comes to the description for a property, the way that those properties are defined is a very specific kind of legalese, and I'll show you a couple project descriptions a little bit later on through the term as well. But it very much kind of reads like almost like a story. It's like the property line starts here, it goes at this bearing for this amount of feet. Sometimes in these old property definitions, it'll say up until like this tree or up until this fence, things like that. These kind of interesting descriptions. That's another way, especially like property lines are going to be defined as by a legal reference or a legal description. So here's a small excerpt of like a property survey. And you can actually get examples of these for like tax lot definitions and tax lot maps. With those legal definitions off of Portland maps. And then a vertical reference. And so this is simply just oftentimes a separate system. And I know my image is obscuring the monument image in the bottom right-hand corner. It's the same as I had up before when I showed you the city of Portland's benchmarks. And so oftentimes the horizontal geometry will be controlled separately from the vertical geometry. And oftentimes we have to specify both. So oftentimes when we talk about like what coordinate system or reference system are you using, it is a combination of some horizontal control and vertical control as well. You'll often see that, and you'll see a couple of examples when we talk about projections and coordinate systems a little bit later on in the term. All right, so when we go out and we do surveying, or when we hire somebody to go out and do it, there are some pretty typical measurements that we're going to be taking. Distances and angles are really the name of the game for the most part. We'll be identifying points as well, but to identify those points, we get to that point by starting at a known point, then measuring a distance and an angle to get there. So the top view that you see here, this is like a profile view. This is looking at the side. So in this case, up is really up. So here we have like a instrument at this location right here. And there's a little bit of a typo. It says slop distance, but it means slope distance. We could measure a distance at an angle, or we could stick to just vertical and horizontal distances. That's another way to measure that makes some of the modifications or adjustments not necessary. We'll talk about that, especially when we get into taping and theodolites and total stations. But distances and angles, whether they're horizontal or vertical, are very important and kind of part and parcel to almost every single survey that we would do. The view at the bottom, that's like a plan view looking down, and this would be an example of doing like a traverse, going around and closing a traverse, finding a closed polygon, making sure that you're measuring both vertical distances and horizontal distances. And specifically the reason I brought this up is that it shows the horizontal angles as well. So not just the angle relative to vertical, but also, east-west, side to side. That's an important thing for us to measure as well too. So really all three dimensions are important. but we usually work our way around by simply measuring distances and angles. And so a lot of trig, I mean, is really what I'm getting at. You got to be really comfortable with your trigonometry. Right angle trigonometry is most of it, but also things like law of sines, law of cosines are going to come in handy as well. We already mentioned geographical coordinates, but just to kind of drive the idea home, if you're doing a geographic reference system like a geodetic survey, um, I expect that everybody understands what a line of latitude and longitude are, how they differ. Latitude lines are all parallel. Longitude lines all pass through the North Pole and South Pole. I want you to understand that the Earth is not a perfect sphere, it's an oblong spheroid. But right now we won't be doing a lot of calculations with geodetic information, but that'll change as we get a little bit further through the term. Common units, so nowadays in surveying, for the US customary system, we use the International Survey Foot. That's been used since 1959. The older one we just call the US Survey Foot. They're pretty much the same. The difference is very, very small. In fact, it's only like 6/1 millionths of a meter. Pretty small, but if we're talking about thousands of miles potentially, that could make a pretty big difference. So that's an important thing to understand. Some systems will use international feet, IFT. Some will use US survey feet, which is either abbreviated SFT or just feet by itself. Common other units that you're going to see, like one chain. The standard chain is 66 feet, and we're going to see why that is what was used to define the acre. It's 43,560 square feet, or 10 square chain. So 10 times 66 squared would be 1 acre. Angles, you need to be comfortable measuring those in degree, minute, second, or decimal degrees or radians. And so I think that everybody's had physics and everybody's had basic math. But if you have any questions about how to convert between degrees, minutes, and seconds, and decimal degrees, radians, things like that, just set up some time with me. I'd be happy to walk you through it. Your book does have some unit conversion factors you can take a look at. A lot of these show metric as well. We're not really going to do much in terms of metric. I've only worked on maybe 1 or 2 projects in the States that is metric based. There have been attempts in the past to get everybody on the same page as the rest of the world. I don't know if it'll happen in my lifetime, but certainly there are some differences, and understanding how to convert between them is useful. Your book doesn't do a lot of metric in terms of surveying, and again, the majority of people are going to be working in the States, and one unit system is plenty to keep us busy. So, maybe every once in a while I'll toss in a metric measurement or a conversion, but for the most part, you're going to be staying in US customary throughout the term. All right, so when we're doing actual measurements, one measurement could be embodied by this tape measure that you see down below. It's important for us to think about the precision of what we're representing as we take the measurement from the instrument. So in this example here, the top scale on this tape is in hundredths of a foot. And that's pretty typical for engineering measurements. They're going to be in decimals of a foot, hundredths of a foot. On the bottom, you see the traditional feet and inches. That's almost never used in surveying. So we almost never use feet and inches. We almost always use decimal feet instead. And so each of these gradations on that surveying side of the tape are 1/100th of a foot. Now, when you make a measurement and the least gradation is 1/100th of a foot, you will actually specify a value in the thousandth of a foot digit. And that is to, you make an estimate. Oftentimes people would just estimate it as a 0 or a 5. I'm fine either way. Or you might try to make an even more precise guess. The reason that we do that is to help deal with like rounding ties in subsequent calculations. So almost always, if you're reading especially an analog measurement, we can't always do this for digital, is we would represent one additional digit of precision past what the actual instrument can do, and that's an estimate on our part, but it does actually make subsequent calculations more precise or more accurate. All right, hopefully everybody is familiar with significant figures based off chemistry or physics classes that you've taken in the past. Just as a quick reminder, significant figures are any figures, any digits with numbers that are non-zero, except zeros will count if they are on the end of the number on the right side of the decimal or in between two non-zero numbers. Those zeros would count as well too. So all of these examples at the top have two significant figures, right? These zeros right here are not significant. This zero right here is not significant. On the bottom, all of these measurements have three significant figures. So a zero to the right of the decimal point at the end of the number, that's going to count as well. Here we just have three significant figures. These leading zeros don't count. And the significant figures is important. We will, in terms of what professional land surveyors are expected to do, a lot of it has to do with representing error and precision, and significant figures have something to play with that. Now it does get a little bit tricky, and I'll be honest, I don't always know the correct answer when it comes to significant figures, because there's some not standard situations out there. Generally speaking, I try to, if I know that I'm going to be using a value for a subsequent calculation, I'll usually keep an extra digit past the significant figure to prevent any rounding issues when I'm multiplying or doing something like that down the road. Because the significant figures really are most important in my estimation for the final value that you would be reporting. For intermediate values, it's sometimes okay to, if you're going to be multiplying like multiple things together then with another one later on, I often will kind of leave those digits in my calculator. But we'll do a couple of examples to kind of show you what I'm talking about with chained calculations. It's not always as straightforward as it might seem. So basic significant figures rules would be, if you're adding or subtracting, you simply go with the least precision number that governs what your final answer would be. So in the example on the left-hand side, we've got three different numbers being added together. The least precise number has a digit in the tenths digit, and therefore I'm going to cut off the, oops, I went through the 7 there. I'm going to cut off my final answer to be in the tenths. However, I would use rounding here as well too, and so we would represent the final answer as 422.8, because 0.77 would round up to 0.8. Likewise, for subtraction, my least precise number is 378. It has its lowest digit or least precise digit in the ones, and therefore I would round this, and 375.9 would round up to 376. And I'll often put a period after a number, after the ones digit, just to make it really clear. Yeah, I think it's just nice to be verbose about that. It's more important if you have a 0 in the ones digit to put a period there to indicate that it's significant, but either way, the least precise number is going to control when it comes to addition and subtraction. It's slightly different when we talk about multiplication and division. Here, we really care about the least significant number, not the least precise number. That's what's going to end up controlling. So 123.25 has 5 significant figures, 2.16 has 3 significant figures, and so 3 significant figures is going to control for the product, and so I would end up going with rounding 266.22 to the nearest ones digit, which would be 266, because this number right here has 3 significant figures. Likewise with this quotient, I've got, let's see, 7 significant figures on the left. I've got 4 significant figures on the right, so 4 is going to end up controlling, and so I would cut it off right there, 3 rounds down, and so 6.055 would be my final answer with the correct number of significant figures. Important things to point out would be we do use rounding, so whatever the digit is past where you're cutting it off, if it's a 5 or higher, you can round it up. If it's lower than a 5, you can round it down. Now my old surveying professor from Oregon State during my undergrad had a really goofy rule about rounding. He wanted to make sure, because like a 5 rounding up, that means that you're not equally rounding up or down. It's kind of like 52% of turns are right turns or something like that. But either way, he had a weird rule about you would round up if it's a 5 and the previous digit is odd, and you would round down if it was a 5 and the previous digit was even. I don't particularly care. I usually round up 5s, but it's not going to make that big of a difference. Either way would be okay by me. And conversion factors, when you're multiplying conversion factors, like using the unit conversion method, you don't take into consideration how significant the conversion factor is. If you have an option of how many digits to use of the conversion factor, just add a couple more digits of precision to the conversion factor than you have for your least precise number that you're multiplying by, just to avoid any rounding issues down the road. Yep, that's the first thing that I said here in the best practices. Use at least one more digit in your conversion factor than is in the measured value with the least number of significant figures. That just makes sure that our conversion factor is not controlling the outcome of that multiplication. We already talked about carrying one extra digit in your computed or measured quantities. Probably measured would be better here. Measured or observed. And oh no, that says it on the bottom one. So yeah, we're good. So all of these apply best practices. We often leave a little bit more precision in before we get to the final answer, just to make sure that we don't induce rounding issues with intermediate calculations.